Can you hear me talk? I can't tell if my microphone's working. Okay, so that's very weird. Well, I'm here, so hopefully you can see the sights and figure out what's going on. I don't know why my video is not working. I think I'll actually make that bigger sense. Oh. What type of nomenclature would you like, patients? We've done lots of types in class, so I don't know exactly what type you want me to show. Okay, so if you have, and you can practice this in Chem Sketch, if you have, let me make that bigger. Hold on a second. So if you have a priority group and you just have to memorize those, so let's say you have a ketone, that has priority over an alcohol. And so if I have a molecule that has both on it, and I want to name it, I have to name it with the highest priority functional group having the suffix, and everything else needs to go on as a prefix. So, under here, there we go. So in the case of this molecule here, pentanone, it has the hydroxyl group and it has the ketone, that carbonyl. And so the hydroxyl group would be put as a prefix, whereas the ketone gets put as the suffix. You basically just have to memorize that table, but it has, you know, the same kind of pattern for everything. So if I have something with an oxygen, like an OH group, and a nitrogen, okay? So this would be hard for you to name if you don't know those rules, because you would look and not know which one gets the lowest number, because you could number it either direction and both numbers would be, what is that, 2, 2, and 5. So what we learned in class, though, is that hydroxy is more reactive than amine, so it has the higher priority group. So if I circle this, yeah, well, I've been doing this a while, Keely. But if I go through and generate my name for structure, there we go. So you see that the alcohol gets the suffix, whereas the amine gets the prefix, because the amine comes less in reactivity than the alcohol. As far as RNS stereochemistry, I mean, I've given you a billion different examples of that in class, so I'm not sure what I can give you now that would be any different from that, if you don't have any specific questions on that. But you can check it in Chem Sketch. So here, it's the same molecule, but I actually told the Chem Sketch program what the stereochemistry is by showing it in perspective. So now, if I want to, I can go through here and we would look at this and say that it has R stereochemistry, where the hydroxyl group has the highest priority, followed by the large group to the left, then the methyl group, then the hydrogen. So if I go through here, it'll actually tell you that that is the R stereochemistry. So it's the same name, it just has that extra component added to it if you know the difference. Now, something that you won't be able to use this for is for the stereochemistry on rings, because I had you guys learn kind of an older way that's not quite as useful. I'm trying to get enough space to work here. Hold on. Let me move some of this. There we go. All right. So if I were to have an alkene, you can still do the stereochemistry with that. So you just have to put in the double bonds. So for this molecule here, on the first carbon of the ring, that one that's kind of at the top connected to the nitrogen, the highest priority group there is the nitrogen. Oops. And then on the second one, the highest priority group is the carbon. So let's see if I can, there we go. Okay. So if you look, those are both on the same side of the double bond, so that would have to make that Z stereochemistry. And so you would name the molecule just like all the other ones that we've done, but it would tell you that it's the Z nomenclature. Next question. Yes, that's right. Whatever that higher priority group is, that's the one that, I mean, that's why they get designated a priority, so that we know how to name them if there's multiple groups. So that's always going to be the case. There's never going to be a time when that's not the case. With cis and trans, do those prefixes go before numbers or after? So you always put the number that the group goes on, but with cis and trans, we don't really put a number with those. So you would just have cis or trans and then the name of the molecule. Yes, Keely, I actually mentioned that in class, so that's probably in your notes somewhere. We're using cis and trans only in cyclic structures. We're using E and Z for double bonds, and we're using R and S for anything else that's a chiral carbon that's not in a ring. In reality, cyclic molecules, and you'll see this actually if you put it into ChemSketch, but it's a little bit harder. So if you take some sort of molecule that we would normally designate as being, you know, cis-trans, how we've done it in class. So I'll just take something like dihydroxybenzene, or dihydroxycyclohexane. So if I take this, even though we could look at this and say, yes, those are cis to each other, you can actually get real stereochemistry, the RS stereochemistry out of them. And so it'll tell you whether it's R or S. So that's going to be kind of a difference between the way that ChemSketch will do it, which is technically the correct way, but I'm making this exception because it'll make it easier for you guys to do it kind of the old way with just the cis and trans. Pardon me. Just have all kinds of names up here, don't I? Yeah, that's just a difference in, I'm trying to make it a little easier on you guys by doing it that way. Really, we use cis and trans terminology when we're just talking about the orientation, like relative space of two groups. But, and I mean, you know, with this molecule, that cyclohexane diol on there, you would have the RR, the SS, the RS, the SR. You would have all 4 enantiomers for that. So, cis and trans, though, makes it a little easier, I think. We're doing things briefly. What about them patients? Well, she told me that she was going to try and log on at 8, so I thought she was already by her computer. But what do you want to know about SN1 reactions? Do you have a specific question? Yes, I can. So, let me pull up my drawing example here. Hold on. Okay. 1-methylcyclopentanol. Okay. So that would be cyclopentane. Methylcyclopentanol would be this, 1-methylcyclopentanol. Okay. Yes, it's a tertiary carbon. So if I have this molecule that I have drawn here, that methylcyclopentanol, and then I put in sodium bromide, which is really Br minus, right? Because that's going to ionize. And I have H2SO4, which is essentially H plus. I'm just kind of making it simpler here. So what you would have would be the hydroxide, or the hydroxyl group would deprotonate the acid to become protonated. And once you have that, you have made a bad leaving group, hydroxide, which is a horrible leaving group, into a good leaving group. You've essentially made it into water. Now, because this is in a tertiary carbon right there that the leaving group's attached to, because that's a tertiary carbon, you're going to have the leaving group leave first, right? That's what's the difference between an SN1 and an SN2. So I show my leaving group leaving. Oh, that was supposed to be a carbocation, I'm sorry. Let me fix that. Okay. And so now that's a really good electrophile, right? A carbocation is really, really electrophilic. It really wants electrons to attack it. And so fortunately we have bromine floating around because we added sodium bromide, and that is a wonderful nucleophile to work with your electrophile. So that's what you would get. Oh, and Carrie, you can always just, you know, use the name sodium bromide, sulfuric acid. I'll know what you're talking about. Let me... Whoa, that's too small. That's too big. Oh my goodness. Okay, awesome, Carrie. And David, I just got your message. Let me see if it's in my email. Yes. Huh? Yeah, I can't get my... Sorry, guys, hold on. Brandon's here. Brandon, I can't get my camera to work. So, even when I turn it off or on, or it doesn't seem to matter. I can't... Like, they can still hear me fine, but it doesn't pop up with the webcam on any of it. Like, it shows that it's on, but... David, while my husband's working on that, I'm looking at your problems. Okay, so the first one you sent me is an elimination reaction, and we haven't covered those in class yet. And the second one you sent me is an addition reaction, and we haven't covered those in class yet, so you wouldn't be expected to know how to do those. I would imagine you would be very stuck on those because we haven't learned them yet. Yeah, I don't know what's wrong with the thing because I didn't change any of the settings and it was working fine the past 2 times.
They can see this.
Yeah, they can see everything. Okay. They just can't, and they can hear my voice.
Okay.
It's weird. I'm sure they want to see the inside of my closet where we're sitting.
Oh.
Mm-hmm. I fiddled around with the settings, but I couldn't figure it out. Sorry guys, we're having technical difficulties, apparently.
Okay, yeah, I just...
Why is it so tiny?
Oh, it's because of the resolution. I didn't know how big it was going to be.
Okay. Right. I can also scale it.
Groovy. Cool.
Hi, guys.
Toodles.
Bye. Thank you, Brandon. Okay, that's all right. Dr. Man, did you say that a bad leaving group? A bad leaving group will not react. Like, you can't get a bad leaving group to leave unless you make it a good leaving group, like by protonating it first, like we do with the water. And David, can I get a shout out? Did you see what I was talking about? We just haven't gotten to those reactions yet. Yes, like Bad Company, it just won't leave you alone. But David, those are going to be the next things that we learn next week, so stay tuned. That is I like giving you guys my old exams, but that is the drawback of doing that, is sometimes you're like, I don't know how to do any of this. It's just because I haven't gotten there in class yet. We kind of do exams just whenever we've covered enough material, so it kind of differs every semester. Did I miss any questions so far? Oh, Keely, I was going to kind of expand a little bit on what you just said. So, a bad leaving group and a mediocre group. Oh, patience, you kill me. So yeah, let's say you have, let's just come up with a bunch of leaving groups. Let me go back to my paint. Okay. And I'm just gonna select all that, and can I delete? Yes. Okay. All right. So let's say we have a bunch of different types of leaving groups, right? So we have the really, really good leaving groups. That would be things like water. Water's a really good leaving group. Things that are pretty stable on their own is really what we're looking for. Any of the halogens, except fluoride. Fluoride's kind of weird. You've probably noticed it doesn't do a lot of stuff. Iodide, I tell you guys, you cough on it and it pops off. So those are some examples of good leaving groups, okay? So even if you have kind of a mediocre nucleophile, you can get a good leaving group to leave with a mediocre nucleophile. However, and just think about it energetically, right? Let's think about if I had something that was a bad leaving group, like legit bad leaving group like hydroxide. We know that that's really unstable on its own, right? That's why it's super reactive and corrosive if you have sodium hydroxide, right? So if you have something like hydroxide, you're not going to be able to take something as stable as iodide and knock it off. There's no way that that's going to happen. So you need to think of it energetically, right? We have those energy diagrams, and that is such a bad picture. Let me try that again. There we go. I tried using the mouse, and that was a very big mistake, apparently. But, you know, we have to start up high and go low, right? That would be an exergonic reaction. It's that same junk you learned in Gen Chem that you thought you'd never have to see again. But if you go down energy, you're going to be favorable as far as the whole Gibbs free energy thing goes. And that's going to make your reactions happen. Well, think about iodine and hydroxide. Which one's higher in energy? Hydroxide is higher in energy. We know that because it's super reactive. And iodine is really low in energy. So we could basically... Well, that's confusing the way I have that. I'll just take that off and act like it didn't happen. But basically what you're looking at is a molecule. Let's say I had a methyl group with an OH on it versus a methyl group with an iodine, okay? And I have some sort of random nucleophile, even if it's a really good nucleophile. If it knocks off the hydroxide, then I'm going to have hydroxide floating around that's going to be super, super unstable. If I have the nucleophile knock off my iodide, then I have iodide floating around. That's stable enough that you literally eat it in iodized table salt. So I hope that kind of is clear and makes sense, right? You're basically not able to displace a bad leaving group with even a really good nucleophile simply because a bad leaving group is too unstable on its own. At least for the types of reactions that we're doing. You guys might see examples if you try to look it up online. But we do things briefly, so. Keely, was that just like a confusing mess, or does that make any sense at all? Also, who's Ray? We don't have anybody in class named Ray. Ray D? We just have random people joining into the class, don't we? Are the bad leaving groups the ones that make good nucleophiles? Yes. Like hydroxide, methoxide, that kind of thing. Oh. Okay. Rochelle, I will accept that you are Ray D. I'm just sitting here thinking like, we have some random dude named Ray showing up to our class online office hours. Welcome to my closet, Ray. I did this so the dogs wouldn't bother me, because I have a door to close. We can call this dress cam today. These would be my dresses. In case anybody was curious what my closet looks like. Yes. Rochelle, I would expect nothing less out of you. I'm going back to Kim's sketch. I'm sure you guys have more questions. especially because I just got home a few minutes ago. And so they're like, hey, you're home. Let's be friends. I'm like, I got work to do, pups. It won't kill you. It's the same thing every time, Keely. So, you know, pick out your numbers, 1, 2, 3, and 4. Is a cyclohexane with 3 double bonds of benzene. Yes, it is. And there's a reason we haven't covered that yet. Benzene, because of the resonance in the ring, it has really specific chemistry that it does. And we'll talk about that in about 2 to 3 weeks. Okay. Let's think of how to name this molecule. Give you guys a quiz. Give me a second here. I'm gonna... Whoa, that is special. Guys, I think I broke the internet. Okay. Technology is so freaking weird. Display capture. Whoa. Alright. So let me pull back up my chat box. Okay. There was a reason I was... there was a reason I was doing this, I swear. It's just so I could do it the same way we normally do it in class. Make sure that feed still looks okay. Okay. So, let's name us this molecule. Name us this molecule. That sounded so redneck, didn't it? Okay. So... my parent chain would be the cyclohexane because that's what is on there. The parent chain would have whatever the high priority groups are. Oh, come on now. I'm just having a day here. I'm actually going to go ahead and throw cyclohexanone on there because we see that there's a ketone right, whoa. So that purple group is a ketone. So we've got cyclohexanone. if we wanted to number it, we would have to do so in a way that the other groups would have the lowest possible number. So because the ketone is the highest priority group, it would be default number 1, and then the alcohol next to it would be number 2. But because it is a lesser priority group than the ketone, we would have it as a hydroxy prefix. And then next to that, 3, 4, so on carbon 4, there is a 4-chain ring, a 4-carbon chain, if I can even say the right words. So that'd be a 4-butane, or butyl. So someone type that in, tell me what that is. Oh, sorry, David. I didn't know you drove so far every day. Are you still having trouble seeing it? Do I need to try and make things bigger? 2-butyl-2-hydroxycyclohexanone. Thank you, Carrie. Let's see if you're right. Or if I was right. Where's my little... generate name. Ah! Oh, there we go. It seems inconsistent. The chem sketch seems inconsistent with when it decides to put numbers on a ring. So if you looked at this molecule here, right, like, okay, no numbering on the ring. If we put on that, it's probably not going to number the hydroxyl group. Or even if we put on 2. Let's do... something with a lesser priority, like a methyl group. I wouldn't be surprised if this tells us that it's 2-methyl-cyclohexanol instead of putting a number with it. Oh, no, they put it on there. Yes, hydroxys and oxys are prefixes that are going to go on there before the name of the parent chain. So in your notes where you have the table of the prefixes and stuff, come back to this, sorry. Yeah, so in the thing that has the prefixes and everything on that table we put on the board, you can actually write down on when it's not priority, write that as prefix name, and then when it has priority, write that as the suffix name. Yeah, I would still count that, Keely. Absolutely. It seems like that is less standard, and I can't... Sometimes it seems like the program will do it one way versus the other. I've always been told that if it doesn't... If it's like the only way it could go, that yes, and then everything else is alphabetized except the dies and the tries. But I don't understand why... Sometimes it'll put the name with the highest priority group on a ring, and sometimes it doesn't. No stereochemistry because there was planar geometry. If you have planar geometry, you have EZ stereochemistry. If you have something that's SP hybridized, then it's linear geometry and there's no stereochemistry then. if it's not priority, you use it as a prefix, and if it is priority, it's the suffix. Oh, yeah, so just because something has dashed lines and wedges does not make it a chiral molecule, right? So sometimes I'll do that just to remind you guys. Like, let's look at this. This would be an achiral molecule that I'm drawing, because that carbon, there's no carbon on there that has more than 4 different groups on it. All the groups are either a methyl, there's 3 methyls and a hydrogen. So if I go through and tried to name this, it'll just say 2-methylpropane. It won't give you the R or the D or anything because it's not chiral. Okay. Now, if you look at the one over here, this one is, it does have stereochemistry. We don't call it chiral because it's not a carbon with 4 different groups on it. Okay. It has 3 different groups attached to it, but it still has stereochemistry. It's got diastereomers, so you would have the E or the Z possibilities. And when I draw those in here, okay, it'll definitely tell you that there is E stereochemistry the way it's drawn. Now, if I wanted to flip my stereochemistry, right? If I flip those 2 groups, now that should be the Z stereochem. Okay, so now there's another way you can draw that, and some people do it this way because it's, instead of looking at it kind of top down, you're looking at it front to back, and I think I might have given you guys an example like this in class. But if you have something like that, it's still the same orientation and the same stereochemistry still. So it'll still give you that same name. It's just another way of doing the same thing. How would we know to draw the correct molecule with the correct group if you give us one of the 2 that have the same prefix? Well, because you would have, are you talking about a ketone and an aldehyde? You would know because of the number. So, let me delete some of this. Running out of room. So let's take a molecule, let's name something. 2-oxo butanoic acid. Okay. Right. So 2-oxo-butanoic acid. Alright, well, I'll draw off my butanoic acid. David, are you still having trouble seeing this? Is it still too small, or do I need to make it bigger? Let me know if I need to make it bigger, because I can zoom in a little bit. Yeah, they're both basically the same functional group, but in different spots. So this would be my butanoic acid, right? 1, 2, 3, 4 carbons. And then 2-oxo would just mean carbonyl. Right there. So by definition, because it's not at the end, it would be a ketone and not an aldehyde. Now you could have a molecule that has both an aldehyde and a ketone on it. So let's say that instead of the butanoic acid, I used butanal. Oh, hold on a second. There we go. So the aldehyde has a higher priority than the ketone on the list. So it'll still be named as butanal, but it would be 3-oxo-butanal is what it should go with. Yeah. So hopefully that makes sense. Whoa, there's 18 people watching this. That's almost our whole class. I feel popular. How are my eyebrows? If I'm going to be on YouTube, I have to have good eyebrows, right? A carboxylic acid, a ketone, and an aldehyde. Matthew, are you trying to kill me? No, okay, so you would end up with, thank you, patience, yes. So let's look at what Matthew's talking about, because I think that's a really good example. So I'll just take this molecule that we started off with here and add an aldehyde to it. Whoa, come on. Okay, so now it has an aldehyde. Sorry, sitting in a closet's not super comfortable. But so I have an aldehyde, right? I have a carboxylic acid and I have a ketone. So what we would end up with was a dioxo. You would call both of them an oxo. Chocolate milk and popcorn sounds absolutely disgusting, Carrie. But whatever suits you. Somebody needs some apple cider. But so we would still name this as a... How many carbons did we have? 3, 4. We would still name this as a butanoic acid, but now we would have a dioxobutanoic acid. So 2,4-dioxobutanoic acid. The oxo is just going to be generic for carbonyl. I'm glad you're happy. Nothing quite like sitting down in the study watching your professor in her closet while you're drinking chocolate milk and eating popcorn. A leaving lingo. Neat. You're not too old. Did that make sense though, Matthew? Like, it's the same exact rules regardless of how much crazy stuff's on there. Yeah, because this is a skeleton structure, you didn't have to put the hydrogen on, but it's kind of implied that it's there. I don't know if you can see this. When I highlight it, do you see a CH pop up? I mean, we can put it on there if you want. Does this make you happy? And a lot of people with aldehydes just put the hydrogen on there, but you don't technically have to because it is part of the skeleton structure. Thanks, Aru. What's wrong with you guys? You are my special snowflakes. I just opened up the closet door and scared Twinkie. That's not a carbon attached to the hydrogen. Keely, I don't know which one you're talking about. There's a carbon here that's a part of the carbonyl. Oops. So that aldehyde has a carbon right there. Let's see if I can highlight it. Nope. And then this right there's a CH2. See, I'm not sure exactly what you're asking me, Keely. The ending hydrogen has a carbon attached to it. It's the carbon that's part of the carbonyl, the aldehyde. If you were to draw that out as a let me try this. If you were to draw that out as a 1, 2, 3, 4, like a longer chain, which, by the way, you guys are always welcome to draw it longhand like that. So on one end of the carbon has a carboxylic acid. Then there is a hydrogen there. Oh, you know what? I just did that wrong. That's where we had the ketone, then hydrogens, then an aldehyde. So that would be the same molecule, just drawn more like a calculus structure. Yeah, sometimes it helps just to draw it out longhand. And I know it takes a little bit longer, but I mean, my exams are not super long. They're only 4 pages. I think they're the shortest in the department, actually. So you usually have enough time to redraw things if you need to, especially if it's... Some people have certain troubles with more functional groups than others, like carboxylic acids and aldehydes, things that are at the end. For whatever, a lot of people will forget those carbons as part of the parent chain, so... If it helps to redraw it out, because the oxygen, the double bond oxygen has to be connected to something, you know, it's not like just floating. Yes, you should have time to use your model kits on the test. I mean, it's a 4-page test. So you have about 15 minutes on each one. Something you can do ahead of time. Yeah, you can have answers in the calculus structures. As long as the structure you give me is legit, then I count it regardless of how you draw it. But as far as the model kits, some people like to come into the class with something that's chiral already made so that they don't have to, you know, work on that. I think the E and Z is pretty easy to see without a model kit. The cis and trans are obviously easy to see without a model kit because it's either pointing up and down or on the same direction. But if you want to make, you know, a molecule, I don't have my model kit with me, but if you want to make a model kit, would you guys have been impressed if I like pulled a model kit up out of my closet? Like, here's my model kit. But yeah, you can make something that's kind of like a chiral generic carbon and use that during the exam tomorrow if you want. I don't mind bringing that ahead of time. David, that was already... I already emailed them to let them know. Did they say they wouldn't let you? Because there's 2 of you taking it over there, so I told them to make sure that you guys had a periodic table and a model kit. But if that's a problem, you know, because you guys are taking it at the same time I am, tell them to call the chemistry office, and I will give the directions to Miss Donna that... Let me send her an email while I'm thinking about it right now so she has it for tomorrow. But that way they can call and get the confirmation that that's okay. So that is an email sent to Miss Donna, just making sure, because Amanda takes it over there too, so that way, if you guys need the model kit and they're like, you can't use the model kit, then... Yeah, I type pretty fast. I didn't know you guys could hear that. I'm a little embarrassed. For all you know, I was just banging on the keyboard and just making it sound really impressive. Yeah, but yeah, David, I made sure to put that in the email, because they have a section that's like, any other considerations. I'm like, make sure they got model kits and periodic tables, and I've sent them over a periodic table for any of my students. So if for some reason they need one of those also, you know, they have it on file, but you guys obviously have access to all the same stuff in class that everyone else does. Oh, patience. But, you know, I am old, and I've been an academic for a long time. I've had to type a lot of papers. I'm just saying, you know, I've had a lot of practice. I feel like you guys are starting to ask fewer questions. I appreciate you too, Patience. I appreciate all of my students. I think you guys are awesome. I'll take another one. You have me for a few more minutes, but then I have to go and proofread. I have the exam written, I just have to proofread it. Make sure it doesn't have any jacked up stuff in it. I love your optimism, Keely. Good night, Patience. Oh my gosh. Well, thanks for staying up to spend time with us tonight, Rochelle. It's always good to have a few questions in. And I'll be in, you know, my office tomorrow also, before the exam, so. Oh my gosh. I have faith in you. They have the product and you ask for the start. I mean, I'd have to give you some sort of indicator as to what type of reaction we're looking for. And so far, we've only had 2 types. So things that I'll give you 2 out of the 3 parts of reaction, right? So you have your starting organic material, your product organic material, and then kind of whatever else would go over the arrow, like sulfuric acid, sodium hydroxide, that kind of thing. Or an acid-base reaction, right? Like what type of acid? You'd have to have an acid and a base, right? To give something. So I usually will give reactions where there's a question mark, but there's only 1 question mark per reaction. I can't just give you a single molecule and expect you to read my mind and know exactly what reaction I'm talking about. Twinkie, did you find a squeaky toy? Oh, hi, Red. Here's Red Dog Cam. Whoop. This is why all of my clothes always have dog fur on them. If anybody was curious, that's the reason. You were the reason I can't have nice things, Red. Red decided to get a squeaky apple out. He has this really cute toy that is a little apple. His blood work came back good, actually, Keely. Thanks for asking. Go. They don't want to hear this. This is why I'm in the closet. Go. Close and lock the door. Yeah, they said he had unremarkable blood work, so they're not thinking it's anything terribly serious, it sounds like. So, yay! Alright, any other questions? I'm gonna hop off and finish writing that exam for y'all. I'll be in tomorrow at 10:30-ish, 10:15-ish, like normal. I have my class at 11:30, and then I have another one at 12:20, and then I get a break at 1:15. So, unless Dr. Sullivan grabs me and takes me to lunch with her like she's been doing the past few Fridays, I should be in my office during that time as well. So you guys can come and ask me questions. You are welcome. You guys are awesome. I'll see you tomorrow, okay? Bye.